Hello, everyone. In the previous section, we talked about Taylor polynomials. Um, and now, in this case, in this section, we get to talk about properties of power series. So, not Taylor series, that's a typo. All right. And so, let's discuss some properties of power series. The first one observation that I want to make is something about our geometric series. So recall that our geometric series tells us that I have this equation that the sum from k equals 0 to infinity of r of k equals 1 over 1 minus r, where r is less than or equal to 1. In which case, the reason why I don't have an a is because my common factor for a is 1. Well, in this case, I can actually replace that geometric series formula with a function if I replace r with x above. And now I have a function representation where I can now rewrite the function 1 over 1 minus x as the sum k equals 0 to infinity of x of k when the absolute value for x is less than 1. Now this is important because inside here I have a polynomial, and just like in the previous section where I said for a Taylor polynomial, I get a better approximation of the function as I add more, as I make the power go higher. Here I went one step further and I said, let the power go to infinity. And so that's going to be an observation, especially when we get to section 11.3, that as n goes to infinity, f of x can become a power series. And I'll just write the general expression below. And we'll talk about in session 11.3 that those power series have a special name called Taylor series. But before we talk about Taylor series and all of that jazz, we need to discuss properties of power series. The first question is, when does a power series converge? Because in the previous chapter, we spent a lot of time discussing about when series converge or diverge. And now that we have a brand new type of series called power series, we need to know when that power series, when it will converge. And so let's go over theorem 1. So if I have a power series, there are only 3 ways that this is going to go. Either the series will converge only when x equals a. It will converge for all x, which means that for any x in the interval negative infinity to infinity, no matter what, my series will always converge. However, 1 is too strict of a policy, 2 is too loose of a policy. So let's go with the most common theorem, or the most common way, to show convergence, which is number 3. Is that there is a positive number r such that I converge if the distance between x and the value that I'm centering my power series, if that distance is less than r, and it's going to diverge. So converge if it's less than r, and diverge if it's greater than r. So here's why that is important. This definition absolute value. While it doesn't look like it, this gives us an interval, which means that we have an interval in which my series can converge or diverge. So let's dissect in case 3 what that interval is going to look like. Okay, so in case 3 we say I converge when there is a positive number r, capital R, such that the distance between x and a is less than r. Well, one way to rewrite an absolute value is that anything inside the absolute value is greater than the negative value of that constant r, and is less than the positive number r. And if I add all sides of this inequality by a, then what I get is a minus r less than x less than a plus r. And this forms my interval, where x is in the interval a minus r, a plus r. Now, the caveat with case 3 is that there can possibly 4 scenarios occurring. Case 1 is where I don't include the absolute value, or I don't include the endpoints. The second case is I include the left endpoint, but I do not include the right endpoint of that interval. Third scenario is I don't include the left endpoint, but I do include the right endpoint. And then the fourth case is I include both the left endpoint and the right endpoint in the interval that I just formed. And the reason why those 4 intervals are important is when x is in the interval, the power series converges. And that's the power of a power series. It's not convergent everywhere, but in a very small interval, my power series will be convergent. And so before we go on with some examples, let's go ahead and dissect and give us some definitions. The number r that we saw in Theorem 1, from now on, the name that I'm going to give that is called the radius of convergence. And the idea you can think about the radius of convergence is that the distance of any input from my power series to the center A cannot exceed r. And when you draw that out, you form essentially a circle with a radius r, and that's why it's called the radius of convergence. Now, the work that we did in this page to get which intervals x is, that interval also has a special name, and that is called the interval of convergence, which in this session I will abbreviate as IOC. That is the interval in which all values for x will converge. So, as we mentioned for case 3, there are 4 scenarios for my intervals of convergence. And that interval of convergence is, I don't include the endpoints, I include either the left or the right endpoints, or I include both of them. But let's briefly talk about cases 1 and 2 so we can do full coverage of everything. So case 1 in Theorem 1 says, I only converge at one point. And so since I converge only at one point, and that point at A, and if I plug in A for x and do A minus A, I get 0. And so if we get a power series that converges only at the point that I centered my power series at, the radius of convergence is 0. And we don't really have an interval of convergence because it's just the point A. Now the second case is I converge for all x that I could pick. As I noted before, that means x is in infinity over infinity, which means that my interval of convergence is all real numbers. And because my interval of convergence is all real numbers, I don't have a stopping point in which I have to stop. So my radius of convergence in case 2 is positive infinity, to make me know that I have no stopping point in which my series will converge or diverge because I converge everywhere. And then in case 3, we have to be specific with our radius of convergence r and use one of these 4 cases. All right, and so before we go on, let's go ahead and draw a photo. So this is a photo of what's going on. The theorem 1 is saying, if I am inside this distance, I am convergent, and then I'm divergent outside. So what this photo is saying is this part in green, that is my interval of convergence, which means that I converge when I'm inside this interval, and I diverge when I am outside the interval. So, power series, to emphasize, diverges outside interval of convergence. And it doesn't matter from the right or from the left. If I am outside that small interval of convergence, my power series will diverge. Now, the caveat is in 1080, power series is still a series, so I still need to figure out and determine when I converge or when I diverge. Typically, the ratio or root tets are going to be our best friends in this scenario. And essentially what we know is, I know what makes these 2 tets convergent. And what makes them convergent, to give you a recap, if we're doing ratio test, it's the limit as k goes to infinity of the absolute value of a of k plus 1 over a of k less than 1. And then if it was the root test, it would be the kth root of the absolute value of a of k is less than 1. And the reason why I want to re-emphasize is the way that we're going to find the radius in intervals of convergence, typically, is we're going to use our known test, and we note when I'm convergent or divergent, and we're essentially going to solve and get it to be in the case 3 where x minus the value that I centered at is less than something. So with that, let's go ahead and test it out and find the radius and interval of convergence for our first series that we talked about. So first thing I want y'all to note, keep in mind that no matter what, once I see an x raised to the k, it is still a power series, which means it must abide by that rule in that form. Now note that I don't have any coefficients up front, so that means c of k is just 1. And because it's just x raised to the k, that tells me that my power series is centered at 0. So for yes, I'm not going to do the ratio or the root test because we noted above that this is a geometric series where I just replace r with x. So because of that, I'm going to make that note now. That recall that yes is a geometric series and we recall what makes a geometric series convergent. And for a geometric series to converge, we need the absolute value for x to be less than 1. Since my center is 0, I can rewrite that. So, recap for math terminology. If I write a big arrow with both arrow endpoints here, that's my shorthand of saying equivalent. To follow our form, that's s less than 0 equals less than 1. And so let's now go back to our theorem 1. I converge when the absolute value for x minus the point that I'm centering is less than some constant. And now, in example 1, I have x minus the point that I'm centering at less than some positive number. So in this case, my radius of convergence will be 1. And now we go ahead and figure out what the interval of convergence is. We call that absolute value less than something. It's the same thing as me saying -1 less than x less than 1. So our preliminary interval convergence is -1 to 1. Now, the thing about when you form your interval of convergence is you always have to ask yourself, do I include the endpoints? And the way that we verify whether or not we include or not include the endpoints is we plug in our endpoints into our series and determine whether or not I have a convergent or divergent series. However, since we note that we have a geometric series, I'll go ahead and state no, and the reason why is because recall that for a geometric series, it diverges when the absolute value of x is greater than or equal to 1. And so if I plug in -1 or 1 into my series, into my power series for x, I will essentially have it to be in the point where my series will diverge. And so in example 1, I do not include the endpoints, and so my interval of convergence will be -1 to 1, open brackets, on the left and right endpoints. All right, let's repeat this exercise with example 2. Now, we have -3 to the kth power times x to the k x minus 1. And so because I see x to the kth power, for this example, I'm going to try the ratio test. But just note that you can also use the root test here. Now, keep in mind that for these examples, I'm not doing, I can choose which of the two tests I want to use. So let's figure out and do the test here. All right, so like we do for ratio tests, let's go ahead and list out a of k and then a of k plus 1. So a of k will be negative 3 to the kth power times x to the k over square root of k plus 1. A of k plus 1, that means wherever I saw a k, I replace with k plus 1. So negative 3 to the k plus 1, x to the k plus 1, and then k plus 1, which simplify down, will give us k plus 2. Alright, and let's figure out our L. Recall that for the ratio test, it is the limit as k goes to infinity. A of k plus 1 over a of k, which equals, after plugging everything in, a of k plus 1, which is negative 3 to the k plus 1 power, times x to the k plus 1 over square root of k plus 2, times the reciprocal of a of k, which is square root of k plus 1 divided by negative 3 to the kth power x to the kth. And let's start simplifying. I have an x to the k in the denominator, x to the k plus 1 in the numerator. So that simplifies down to just x. Negative 3 to the kth power in the denominator, negative 3 to the kth power in plus 1, k plus 1, in the numerator. So that simplifies down to negative 3. So let's clean up. I have limit as k goes to infinity of negative 3 times x times the square root of k plus 1 divided by the square root of k plus 2. Now, keep in mind that I'm taking the limit of k. I'm not taking the limit of x. So for all things considered, this is treated like a constant. So keep that in mind that later on, that constant will be taken outside of the limit. But the first thing I'm going to do is I have a product of two numbers, absolute value. Absolute value of a product of two numbers, I'll summarize it here, is the exact same as the absolute value for the first number times the absolute value of the second number. So I'm going to go ahead and rewrite that as limit as k goes to infinity, absolute value of negative 3x times k plus 1 to k plus 2 is always positive, so I don't need the absolute value. Because this is square root, I'm going to go ahead and put all of that inside a square root. I'm going to use my property absolute values again to rewrite this as 3, because absolute value of negative 3 is 3. But because I do not know whether or not x is positive or negative, I'm keeping the absolute value with it. Alright, and since that is a constant with respect to, with respect to my limit, I can take out 3 times absolute value for x, evaluate the limit, as k goes to infinity of the square root of k plus 1 over k plus 2. And we know from what we've learned in 1060, that whole thing will be 1. which means my entire fraction, or my entire limit, is 3 times the absolute value for x. Now, let's summarize. Since I did the ratio test, I know my series converges if L, or that limit, is less than 1. Because we had 3 times the absolute value for x left, that's the same as me plugging in 3 times the absolute value for x is less than 1. And then if I divided both sides by 3, I get absolute value for x is less than 1/3. Alright, and now my center was at 0, so I note that my center was 0, which means my radius of convergence is 1/3, because remember, radius of convergence is the number that pops up, which is the distance between x and the original and the center, which I'll go ahead and write 0 to make it more clear, is less than that number. So radius of convergence is equal to 1/3, and my current interval of convergence is negative 1/3 to positive 1/3. Now I'm not putting the open and closed parentheses yet, because I still need to verify whether or not I include the endpoints in my interval of convergence. So let's verify that real quick. So let's go ahead and verify the second one. So this is example 2, continue. And to verify, since I know my 2 possible endpoints, I'm going to plug in each of them separately, and I'm going to determine whether or not my series will converge or diverge as a result. So if I plug in negative 1/3 into my original series, I get the sum starting at 0, ending at infinity, negative 3 to the kth power. Now instead of x of k, I'm plugging in negative 1/3. So instead of x to the kth power, it is negative 1/3 to the kth power divided by the square root of k plus 1. Now in the numerator, I have a negative 3 and a negative 1/3, both raised by the same power k. So I'm going to use my property of exponents that says I can combine 2 different things if they have the same power, if it's joined by multiplication or subtraction, or multiplication or division, my apologies. And I note that that simplifies down to just the sum k equals 0 to 1 over k plus 1. And now, because I simplified down, I need to determine if this series converges or diverges. And the reason why I need to note that is if it converges, then that means I include the negative 1/3 in the interval of convergence, because that tells me that negative 1/3, my series is still convergent, so it's still fair game for me to do that. However, if I conclude that the series diverges, then that means negative 1/3 is not included in the interval of convergence. And recall from when we talked about series back in chapter 10, I have an algebraic function here, and so I'm going to try to compare with a p-series. And the quickest way to read what p-series I want to compare, highest power in the numerator, highest power in the denominator, take their ratio. So that means I'm going to do a comparison test, and remember, out of the two comparison tests, limit comparison test is your best friend, because we don't have to do that hiccup from before. And let's do our limit comparison test. Again, the series we're going to compare is read off the highest power in the numerator and the highest power in the denominator, in which case I get that the series I want to compare with is square root of 1 over k, where I guess this might be of k. And let's note that it diverges because it is a p-series with p equals 1/2 less than 1. Alright, so that means my hypothesis is that the series 1 over the square root of k plus 1, my hypothesis is that that series will diverge because the series I'm going to try to compare with diverges by p-series test. So let's verify the limit comparison. For a limit comparison test, I'm going to take the limit as k goes to infinity of a of k over b of k, which I get to be the limit as k goes to infinity of what I define a of k to be, which is 1 over the square root of k plus 1 divided by 1 over the square root of k. Dividing by a fraction, same as multiplying by its reciprocal. So I get that equal to the limit as k goes to infinity, square root of k over square root of k plus 1 equals to the limit as k goes to infinity of k divided by k plus 1, which we talked about to be 1. So that is a finite answer. Therefore, let's write our conclusion. Since we know that the series 1 over k to the 1/2 diverges, therefore by the limit comparison test, the original series that I had, 1 over square root of k plus 1, diverges. And because that the power series, when I plug in the left endpoint, diverges, what that means is that negative 1/3 is not included in the interval of convergence. All right, and let's go ahead and conclude something similar with the right endpoint. So now wherever I saw x in my power series, I'm going to plug in 1/3. I get that that is sum goes to 0 to infinity, negative 3 to the kth power, 1/3 kth power divided by k square root of k plus 1. And if I do the same work that I did in the previous step, I get negative 1k over absolute value of k plus 1. Alright, now that I see a negative 1 to the kth power, it tells me I have an alternating series that I'm working with. So because of that, I'm going to try and see if the alternating series test will work out here. So first thing, I need to figure out if I'm non-decreasing or decreasing. Easiest way for me to think of that is let's plug in the square root of x plus 1. Note that you can do the inequality game, but I think that for most situations, marrying it with a function and taking the derivative will be the easiest one to do. And because I'm now marrying it with a function, domain is 0 to infinity. Take the first derivative. If you take the first derivative by moving that over, you'll get negative 1/2. X plus 1, negative 3 halves power, or negative 1 divided by 2 square root of x plus 1 cubed. And I don't care what number you plug in to my domain, you're going to get a negative number for all x in 0 to infinity, which tells me that the function is decreasing, which tells me that my positive portion of the sequence, which, to make it clear, my positive form of the sequence is 1 over the square root of k plus 1. That tells me that is strictly decreasing. So first condition is good to go. Second condition, take the limit as k goes to infinity of b of k, which is the limit k goes to infinity of 1 over the square root of k plus 1. And because k is in my denominator and there's nothing in the numerator to overpower it, that thing's going to 0. So the second condition for alternating series test is now fair game. Thus, the series converges by the alternating series test, which means we include x equals 1/3 in the interval of convergence, because that means that plugging in the right endpoint still gives me a convergent series. So now let's go back to our interval. Because I now know that the left endpoint will give me a divergent series and the right endpoint will give me a convergent series if I plug in, I want to do an open bracket on the left endpoint and a closed bracket at the right endpoint to note that I can include the right endpoint but not the left endpoint. All right. So let's try out now example 3, in which case we are now trying to figure out, let's erase this to make that more clear, the radius of convergence and the interval of convergence for that series. K to s plus 2 to the k power 3 to the k plus 1 power. So if I see a 1 with that x, don't be worried. I can still find my center very quickly. And the reason why, I can still get it into that form for a power series because addition is just a subtraction of a negative number. So that tells me that my center for this series is -2. And for this example, I'm going to put the radius of convergence and the interval of convergence over here. All right. Again, if you want to, you could do the root test for it. In this example, I'll do ratio test again. So I'm going to try this with the ratio test. Let's list out a of k, which is k x plus 2 to the k power divided by 3 to the k plus 1. And then a of k plus 1, everything I saw like k, I replace with a k plus 1. So k plus 1 times x plus 2 to the k plus 1 power divided by 3, because I had a k plus 1, now I have a k plus 2 power. Alright, let's figure this out. We have L equals the limit as k goes to infinity of absolute value of a of k plus 1 divided by a of k equals the limit as k goes to infinity of a of k, which I have to be k plus 1 x plus 2 to the k plus 1 power divided by 3 to the k plus 2 power divided by the reciprocal of a of k, which is 3 to the k plus 1 divided by k x plus 2 to the k power. Alright, and let's do simplification. K plus 2, k plus 1, I have 1 extra of 3, so that simplifies down to 3. S plus 2 raised to the k, s plus 2 to the k plus 1. That means I have an extra k plus extra s plus 2. So that simplifies down to an s plus 2. Alright, and that means I now have limit as k goes to infinity of, let's move everything that does not have a k over here, so that means x squared plus 2 over 3 times k plus 1 over k, absolute value. Just like in the previous example, I'm going to multiply this by product two absolute values. And because this is a constant with respect to k, that means I'm going to move that outside of my limit. So let's do that step. I get 1/3 times x plus 2. Keep in mind, I'm keeping the absolute value with the x plus 2 because I don't know yet whether or not that quantity is positive or negative. Times the limit as k goes to infinity. Now, because k plus 1 and k is already positive, I'm going to go ahead and remove the absolute value and evaluate it. And because I'm taking k to infinity, I take the ratio of the leading coefficients, and so I get 1/3 x plus 2. Absolute value. Now, just like before, because I used ratio test, I know when this series is supposed to be convergent. I know I'm supposed to be convergent when I am less than 1. Because I have a constant of 1/3, and because that 1/3 is positive, it's not going to change the direction of my inequality. So I'm now going to multiply everything by 3 to give me absolute value of x plus 2 is less than 3. Because a, or -2, is the center of my power series, I now have the distance. Let's rewrite that as x minus -2. That tells me that x minus the center of my power series is less than some positive constant, which tells me that my radius of convergence is 3, or that number r. Let's go ahead and figure out what our interval will look like. By properties of absolute value, because it's absolute value less than 3, that means -3 is less. then x plus 2, which is less than 3. Subtract everything by 2. And I get that x is between -5 and 1. Which tells me that my interval of convergence is -5 and 1. However, I do not know yet if I include the endpoints or not. So now we're going to determine whether or not we can or cannot include the endpoints. And I'm going to do that on the untitled page. So, this is example 3 continued. Just like with the previous example, I'm going to plug in the left endpoint. Let's write continued. So x equals -5. And that means wherever I saw an x, I can plug in -5. So sum k goes to 0 to infinity of k, -5 plus 2 to the kth power divided by 3 to the k plus 1 power. -5 plus 2 on a good day better give me -3. And so now I have k equals 0 to infinity of k to the -3 to the kth power divided by 3 to the k plus 1 power. So, because of that k plus 1 power, that means I have an extra 3 that I include there. But I have 3 to the k, -3 to the k, so I can combine them to give me k equals 0 of k over 3 of -3 over 3 to the kth power, and that simplifies down to a -1, which gives me that my overall series, after I plug in the left endpoint, is the sum k to 0 of k to the -1 of k, and because 1/3 is just a constant, I move the 1/3 out. Now, keep in mind that I cannot use the alternating series test. And I cannot use the alternating series test because I failed to satisfy any of the two conditions. A b of k would be k, and that guy will always increase. So the first condition of alternating series test is not satisfied, which means I gotta try something new. But with that, here's my note. If I take the limit as k goes to infinity of k, I get infinity. And from what we talked about previously before, limit as k goes to infinity of -1 to the kth power to over k, that means it does not exist. And on a good day, that's definitely not equal to 0. Thus, the sum k goes from 0 to infinity of 1/3 on the outside, k to -1k on the inside. This series diverges by the divergence test. Which means I do not include -5 into my endpoint. Alright, and now let's do that again by plugging in 1. Plugging in 1 where I saw an x gives me sum k 1 plus 2 to the kth power over 3 to the k plus 1. 1 plus 2 is 3. So I now have sum k equals 0 to infinity of k 3 to the kth power over 3 to the k plus 1 power. Simplified, I get a 3 in the denominator. And so I get 1/3 absolute value or sum of k. And as we talked about previously, we know that the limit of k is infinity, which is definitely not equal to 0. So not equal to 0. So what that tells me is that my series k diverges by the divergence test. Which means, back in our original example, that means my power series will diverge if I plug in either -5 or 1. So that means it's going to be an open interval. All right, and with that, let's go on to example 4. So I chose example 4 because now we're going to deal with a old free response problem. So this was on test 3. And in particular, this is free response 4, fall 2019 exam. So let's go ahead and learn how to tackle that with this series. Okay? So if you look on the solution key for test 3, Dr. Berg used a ratio test. But here, I'm going to actually try to tackle this and show there's more than one way to tackle that guy. So before we do the root test, let's go ahead and do a summary. Because I have x minus 2 to the kth power, I immediately know that the center of my power series is 2. And now with the root test, L is the limit as k goes to infinity of the kth root of the absolute value of a of k, which will be the limit as k goes to infinity of the absolute value 3 to the kth power x minus 2 to the kth power divided by k to the 1 over k. Alright, and so now I'm going to take the 1 over k root of 3k, x minus 2 to k, and then k. K root of 3 to the k will just left me with 3. K root of x minus 2 will just leave me with x minus 2. And the k root of k will just be k over the 1 over k power. So with that, I'm going to rewrite that as, because x minus 2 and 3 are just constants with respect to k, 3 times x minus 2. Keep in mind that that is absolute value because I don't know if I'm positive or negative, times the limit as k goes to infinity of 1 over k to the 1 over k power. So 3 absolute value x minus 2. I'm going to take the limit of the denominator and recall from when we talked about the ratio test, this is one of our 4 limits that have a special result. And the special result for that is that equals 1. So I now have 3 times the absolute value of x minus 2. Now keep in mind that for a root test to converge, I need that limit to be less than 1. So right now I have the absolute value of x minus its center, which is 2, less than a number, but I have a constant of 3 multiplied to that. So I'm going to divide by 3 to give me 1/3, and to also give me that the radius of convergence is 1/3. Okay. And now with that, I'm going to do our work from before. Get negative 1/3 less than x minus 2 less than 1/3. And then I add 2 to all three sides of that inequality. And I'll get 5/3 less than x less than 7/3. Or add, not subtract. Add all sides by 2 to give me that. So that means currently I know my interval of convergence is 5/3 to 7/3. I do not know yet whether or not I should include the endpoints. So let's figure that out. First, let's see what happens when I plug in 5/3 for x. So this is example 4. I'm going to plug in x equals 5/3 wherever I saw an x. Okay, so that is the sum. K goes from 0 to infinity, 3 to the kth power of 5/3 minus 2 to the kth power. 5/3 minus 2 is just negative 1/3. So I get that equals to the sum, k equals 0 to infinity, 3 to the kth power, negative 1/3 to the kth power over k. I get to use my property from before to note that 3 times negative 1/3 is negative 1. And because I have the same exponent k, I can combine to give me negative 3 over 3 to the kth power over k. And everything in here simplifies down to a negative 1. And that's something that we've recognized before. This is our alternating harmonic series from way back in section 10.6, which we know converges. Okay, so that means I'm going to include 5/3 as one of my endpoint as inside my interval of convergence. Now let's plug in 7/3. The sum goes from 0 to infinity of 3 to the kth power. 7/3 minus 2 to the kth power over k. 7/3 minus 2 is just 1/3. And doing the work that we did previously, I just get 1 to the kth power. But 1 to the kth power is just 1. So 1k. Oh, and I forgot that my series started at 1 and not at 0. So let's go ahead and replace everything with a 1. There we go. And the same thing for here. All right. And with that, I recognize that this is my harmonic series. Which we know diverges. All right, so that means in our example, I include the left endpoint, but I do not include the right endpoint. And so that means my overall interval of convergence will be 5/3 to 7/3 with a closed bracket on the 5/3. All right, and now let's go on to some further properties of a power series in which we can combine power series via addition, subtraction, raising by a power, or a composition. And so let's talk about that. So let's suppose we have two separate power series. The first power series with C of k, that will converge to f of x, and the power series d of k will converge to g of s on the interval. So, when I'm combining a power series via sum and difference, the first property is going to be the straightforward one, in which case I'm going to add my two power series, and because I already have x to the kth power, the only thing that we'll be doing is I'm going to add and subtract c of k times d of k, plus or minus d of k. And that's just to denote that I factored out x of k already. And what the first property is saying is, if I have two power series, and if I add or subtract them, they're going to converge to my function f of x plus or minus g of x. Now for powers. So let's say that I have, in this scenario, let's say I have c of k, x of k. On the outside I have x to the m power. And what the first part of this theorem is saying is I'm supposing m is the integer such that k plus m is still non-negative, so that I can move the x to the m inside my power series to give me c to the k x to the k plus m. And if that is the case, because I already know that the power series c of k x raised to the k converges to f of x, I expect this to converge to x to the m power f of x for all x equals -0. Now, when x does equal 0, then my series will converge to the limit as x goes to 0 of x to the m power f of x. And the reason why this is included is if I plug in 0 into x, I might get 0 times whatever the function is at 0, which may not be accurate to what I actually conclude. And so to do that, I'm going to take a limit and see where I head to for that. So keep in mind that we add that technicality because if I do include 0, I'll have 0 times f of 0, which when we're trying to approximate f of x, we might be off by a lot. So we do eliminate that scenario. All right, and so now let's say I have h of x equal to x to the m, b times x to the m. And let's just say that now we have a new power series where in my original power series, instead of x to the k, it's going to be h times x raised to the kth power. And what this tells me is this power series will converge to f composited with h of x. And so what this third theorem is saying to us is that we could take a composition of a power series and it's still convergent. That's what that is telling. That's what number 3 is telling us. And the reason why these 3 are useful is because we can combine and form brand new power series in order to approximate. Alright, so let's do that with example 5, part A. So I'm going to go ahead and use the fact that 1 over 1 plus x can be rewritten as a geometric series. And so now I'm going to form a brand new series with x to the 5th power divided by that. So I know nothing about x to the 5th, but I do know some things about 1 over 1 minus x. And that is, I can rewrite as a power series. Using the information I'm given, I can rewrite that as the sum k equals 0 to infinity of x to the k, provided that x, absolute value for x is less than 1. Now I'm going to use property 2 because in this case m equals 5, and if k is going between 0 to infinity, k plus m equals 0. So that means I could do the valid operation in the part 2 of the theorem that says I can move x to the 5th inside the power series to give me sum k equals 0 to infinity of x to the k times x to the 5th, or sum k goes from 0 to infinity of x to the k plus 5. So what this tells me is, this gives me a new power series and typically we will have to worry about our new interval and radius of convergence, but in part A of example 5 I don't have to worry about that because I still have a geometric series. So the note is radius of convergence and interval of convergence are the same because I still have a geometric series. So this is one of the cases where I don't have to worry about anything changing with my power series. But in part B, I actually do have to worry about a change. So let's try to do this example again, but with 1 over s plus 2. So I want to relate it to the series 1 over 1 minus x, which I know is a geometric series by now. So let's try to rewrite it as such. So I need 1 minus x to appear, 1 minus something to appear in my denominator. Because I have a constant of 2 being added, that means I need that guy to be factored out in the denominator. So that means that's equal to 1/2 times, factor everything out, I have a 1 from factoring out the 2 here, plus x minus 2. Alright, and now what that means now is I need 1 minus something to be in here. Well, I have a plus. I could always rewrite a plus as minus a negative number. So I'm going to do that and do 2, 1 minus x over 2. Now, I say now we can go ahead and rewrite our series because this minus x to the 2, that is being treated as our h of x from part 3 of the theorem. So part 3 of the theorem says I can have a composition where I can rewrite and say if I already know the power series for f of x, then all I do is instead of an x to the k, I replace it with h of x. So I'm now going to use part 3 of the theorem to rewrite, get a little trigger happy with that. And so with that, I get 1/2 times the series k goes from 0 to infinity of not x to the k, but I'm now doing a composition, negative x/2 to the kth power. Again, I'm going to abide by when the series converges or diverges, and because it's a geometric, I'm going to converge when the absolute value for x is less than 1, but instead of absolute value for x, it's going to be absolute value of negative x over 2, less than 1. Or, to rewrite this, absolute value of h of x is less than 1. So in other words, when I'm doing the composition combining of power series, what I'm thinking of is any condition that I had with just x, I'm going to replace with the new function h of x. Now, because I have absolute value and a negative sign up front, this is equivalent to me writing absolute value of x divided by 2 is less than 1. This is the same thing as me saying absolute value of x over 2 is less than 1, which means absolute value for x is less than 2, which means that 2 is our new radius of convergence. Oh, move that up a little bit. Let's move that back down. Which means that our interval of convergence is going to be -2 to 2. And now the reason why I'm not going over plugging in -2 is because if I plug in -2 in for x, I get -1 to the kth power inside there. And because it's a geometric series, recall that diverges when absolute value for x is greater than or equal to 1. And so because of that, I'm not including the endpoints -2 and 2, because if I plug in -2 or +2, I'll get +1 and -1 respectively, which will be in my criteria for a divergent series. All right, and with that, we can now get a combination of different type of those 3 properties, and we'll do it in terms of here. So first thing I want to note, I'm going to separate the x cubed and the x plus 2 as such. We already know what the power series for not x plus 3 but x plus 2. We already know what that power series is by our work from part B. So that will be x cubed times the sum k equals 0 to infinity of 1/2. So I'll rewrite that as, to make it more concise, x cubed over 2 times -x over 2 to the kth power. I'm now going to use my property that says powers on the outside, if it's positive, can go inside. So I can rewrite that as sum k goes to 0 to infinity of -1 to the kth power times x to the k plus 3 power. Now I'm adding the exponents, and I'm going to go ahead and add, let's make that pink to be distinct. And now I'm going to go ahead and move the 2 inside the exponent as well. And if I move the 2 inside the series, I'll have k plus 1 power. Now, keep in mind, even though it doesn't look like it, it is still a geometric series where r is -x over 2. And so because of that, I still have the same criteria of when I have convergence or divergence. So in this example, my radius of convergence is still 2, and my interval of convergence is still -2 to 2, not including the endpoints. And so that's how we combine. Now let's talk about a very powerful property of power series, and that is taking the derivative and the integral of power series. And here's why this becomes powerful. When we talked about integration at the very beginning of the semester, we learned that there are some functions that are very, very difficult to take the integral of. But now that we can talk about a function as a power series by saying rewrite it as a power series, then just take the derivative or the integral of the power series. So we're going to do a strategy called term by term differentiation and integration. And so what theorem free is in a nutshell is saying is if I want to take the derivative of my power series of my function f of x, I can rewrite my function f of x as my power series. And it's the exact same thing as moving that derivative notation inside the power series. Now, inside the power series, I will be doing power rule for each term by term. So that means when I take the derivative of f of x, which is the sum of now the derivative of each of my terms, now what I'm going to have is, for term by term, do power rule here. So we do it for 0, I just have c of k, or c of 0. Let's actually go on the other page to expand that to make that more clear what I'm trying to do. So the derivative, I can now rewrite that as taking the derivative of each term in my power series. So ck times x minus a to the kth power. So that is now equivalent to derivative of when I do 0. So c0 x minus a to the 0 power plus the derivative of when k equals 1. So c1 x minus a to the first power plus the derivative of c0 of c2. Now let's change that to pink. And so on. And now, when I take the derivative when k equals 0, since I have x minus a raised to the 0 power, that equals 1. So c0 will just be a constant with respect to x. So this whole thing will equal 0. This will be c times x minus a. So I just have c1. By using power rule, chain rule with the power rule, I'll have 2 times c2 times an x minus a. And that pattern keeps repeating, which gives us our concise form for the derivative in power series form. And that's why also we start at k equals 1 and not k equals 0. All right, and so with that terminology again, when I take the integral of doing it term by term, Now I'm essentially just doing the power rule for each individual term for that, which is why now I have ck times s minus a to the k plus 1 power, k plus 1, plus my constant. One thing that is confusing here is about that constant c. That constant c is outside of my sum. So I essentially have a power series isolated, and then I have a constant of integration that I just have on the outside. So there are a few remarks that I do want to make. Here's the remark that I have. So I know this property works for finite sums. And so what equations 3 and 4 are saying is I can move an integral in a derivative inside an infinite sum, provided I am working with power series. The reason why I have to add the caveat that I'm working with power series this is not true in general. When you go take more math courses, you'll learn that there are some functions where I cannot move a derivative or an integral inside a infinite series. And so because of that, I'll have to be more careful and specify when I can do that. But for power series, it's fair game. We can interchange back and forth. Now, the second remark that I want to make is that when you take the derivative and the integral of power series and differentiate and integrate term by term, they have a nice property that says the radius of convergence is the same, but keep in mind that I did not mention that the interval of convergence is the same. And the reason why is that's not true in general. Just because the radius of convergence is the same does not mean that the interval of convergence remained the same. There are going to be cases where we will have the original series converge at an endpoint, but when I differentiate, it's going to diverge. Or the original series diverge at the point, but when I integrate term by term, I get convergence. In remark 3, this becomes a very useful tool in your other math courses, in particular when you take Math 2080 next year. This becomes a property that what that property is saying is that you can solve differential equations by differentiating power series term by term and using that solution to help you with nasty differential equations. Alright, and to end this section off, I'm going to do a couple of examples in which I am working with differentiating and integrating power series for that, and I'm going about with it. Alright, and let's finish this with an example. So let's express this as a power series, and keep in mind that the derivative of 1 over 1 minus x equals 1 over 1 minus x squared. So keep that in mind for yes. So what I'm going to do is I'm going to express 1 over 1 minus x squared as a power series. And here's how we're going to do that. I'm going to do 1 minus 1 over x squared. I recall that that is the derivative of, well, that square needs to be outside, of 1 over 1 minus x. And then I recall that I could rewrite s of k, or 1 over 1 minus x, as the derivative of s of k. Now, using our theorem, we could take the derivative and do it by term. So in other words, I can move the derivative inside the summation and do power rule for each individual component. And doing power rule for each one, I have the sum. And keep in mind that for derivative, instead of starting at 0, I am now starting at 1. And now doing power rule, I'll get k times x to the k minus 1 power. And now we still have that the radius of convergence is 1. Let's go ahead and check if the interval of convergence is still the same or not. In this case, let's plug in -1. Well, if I plug in -1, now I have the sum negative, k goes from 1 to infinity, of k of -1, k minus 1. And this series will diverge by divergence tests. Again, when I plug in 1 into my new power series, I just get k. And if I take the limit, we quickly get that this diverges by the divergence test. Okay. And so with that, we conclude that for this example in particular, we still have the same interval of convergence. All right. So I'm going to skip part A for example 7 because that's the exact same work as part B, or as example 6. But now let's say work with that same example, but now let's take the integral of f of x. So in other words, I'm going to take the integral of 1 over 1 minus x dx equals, since I know the power series of that, sum k goes from 0 to infinity of x of k dx. Now, the integral of 1 over 1 minus x, that is, of the following. And if I take the integral of 1 over x using the techniques that we talked about, you'll see that that is the natural log of the absolute value of 1 minus x plus a constant c, because indefinite integral. And to distinguish, I will use c1 to distinguish the following. And on the right-hand side, I'm going to use my theorem that says I can move the integral inside and take the integral of x to the k. Alright, so now I have negative natural log of 1 minus x plus c1 equals the constant k goes from 0 of, now I get to use our theorem that says I'm doing the antiderivative rule with the power rule, and that constant c2 is on the outside. If I subtract both sides by c1, I get c2 minus c1, which I'm going to now call that as my brand new constant. So now I have the integral of f of x, which is negative the natural log of 1 minus x, equals the sum from k equals 0 to infinity of x of k plus 1 over k plus 1 plus c, where here c is c2 minus c1. Now, just like with an antiderivative, we get to have to figure out what's c. And for this, we get to find a value for x such that is easy for us to calculate. In this scenario, I have natural log of plus 1. And so because of that, I am going to now say, oh, well, if I plug in 0, I get natural log of 1, which is 0. So I want to plug in 0 for x. If I do that, I get natural log of 1 equals sum k goes to 0 to infinity of 0 to the k plus 1 power divided by k plus 1 plus c. And I know that yes equals 0, and I know that yes equals 0. And so now I have that 0 equals c. So that means now what I currently have, now let's draw a line to separate our work. I now have that if I divide both sides by the negative sign, that natural log of 1 minus x equals negative the sum k equals 0 to infinity of x k plus 1 over k plus 1. So I now have a series representation of the antiderivative. Now from our theorem, I still have the exact same radius of convergence, which is 1. But now let's check and see if I still have the same interval of convergence. Keep in mind that the original radius of convergence was -1 to 1. Keep in mind that that was the radius of convergence of 1 over 1 minus x. So now let's check and see if our interval of convergence changes now that we have a new series representation. I'm going to plug in -1. If I plug in -1, I get negative. K goes from 0 to infinity of -1 to the k plus 1 power divided by k plus 1. Now, because I have that extra k plus 1 power, I could separate that plus 1 power into just another -1, which means that that negative sign will cancel with that -1, and I'll get the sum from k equals 0 to infinity of -1 to the k power over k plus 1. And I'll go ahead and skip the details and let y'all know this will converge by the alternating series test. But if I plug in x equals 1, I get negative sum k goes to 0 of just 1 over k plus 1. Now I have something that looks very similar to a p-series, so I'll go ahead and let y'all know this diverges by comparison tests. And the series that I'm comparing with is the harmonic series. So that means now we have a brand new interval of convergence where I still have -1 to 1. I don't include 1, but now I include the left endpoint into my brand new interval of convergence. And just like before, with a brand new power series representation and using term by term integration and differentiation, I can now form a brand new power series representation and combine power series together. And so let's do that with the natural log of 1 plus x divided by the natural log of 1 minus x. So the first thing that I want to note is natural log of a quotient is the same as taking natural log of the numerator and subtracting it by the natural log of the denominator. So I'm going to note that. So, yes, we already know its power series. We know that because we did that in part B of example 7. We don't know the first one yet, but just like we did when we were combining power series, this is just my power series that I know minus that. So this is a case where I have a composition inside a power series that I currently know. So I get to use my property of power series, essentially part 3 of theorem 2, that says I can take away, instead of x, I replace it with the h of x, in this case is negative x. Okay, so by using part example 7, I'm going to rewrite the first sum as the power series of k plus 1, but instead of x to the k plus 1 power, it'll be negative x to the k plus 1 power. Keep in mind that this comes from part 3 of theorem 2, where h of x is the negative x. And then as for the first theorem, we have already have that this is my power series. And because I have negative of x k plus 1 over k plus 1, I can have minus and negative. So I now replace that with addition. Alright, so it's not clear what's going to happen right now. And so because of that, I'm going to go ahead and explicitly write out the terms of the first series and the terms of the second series. So negative, wherever we see a k, I'm going to replace it with 0. So negative x over 1 plus, now I'm at k equals 1, so negative x squared over squared plus negative x cubed over 3, so on and so forth. And to keep in mind, k equals 0, k equals 1, k equals 2, and so on and so forth. Now let's go ahead and add when k equals 3 to kind of make it clear what's happening. So x to the 4th over 4 equals 2, k equals 3, plus dot 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 to note that I continue the pattern, plus, now my second sum, and I'm repeating the same pattern, plugging in 0, plugging in 1, plugging in 2, plugging in 3, dot dot dot. So here is k equals 0, k equals 1, k equals 2, k equals 3, and so on and so forth. Alright, so two things are going to happen. Have a negative sign that's going to distribute to everywhere in the first series, and for every even power, the negative sign inside that power will cancel out because negative sign raised to the even power negates the negative sign. So this can be rewritten as, for the first sum, x over 1 minus x squared over 2 plus x cubed over 3 minus x squared over 4, so on, plus, I've done nothing to the second series, so I just get to copy that down. And now I see a couple cancellations going on. I have a negative s squared over 2 plus s squared over 2. Those two cancel. A minus x squared over 4 plus x squared over 4. Those two cancel. And so from what it's going to look like is every term that has an even power gets to be canceled out. And then I'm going to add these terms together. So I'm going to have two copies of each of those terms. So I'll always have a common factor of 2. So I'm going to go ahead and factor out that 2 to give me x plus x cubed over 3 plus x to the 5th over 5 plus so on and so forth. And now let's go ahead and write that in power series notation. So from what the pattern is going to be is that only the odd powers and the odd denominators are going. And as we recalled from when we talked about trig integrals, if my number is odd, I can always rewrite it as 2k plus 1. So my brand new series is x to the 2k plus 1 divided by 2k plus 1, and they all have a common factor of 2. And so now with that brand new power series, let's see if the interval of convergence is different or the same. So recall from the previous example that my original interval of convergence is -1 to 1, where I include -1. So now let's see what happens if I include -1 or if I include 1. So plug in 1 for x, I will get -1, 2k plus 1 over 2k plus 1. So keep in mind that I can rewrite this as k goes to 0 to infinity, -1 to the 2k times the -1 over 2k plus 1. Alright, so for the first -1 term, that's being raised by by even power. So that's just going to be 1. And that -1 is just treated as a coefficient. So I have -2 times the interval k goes from 0 to infinity of 1 over 2k plus 1. I have an algebraic function, so I get to do my property where I just read out the highest power. And if I do that, I'll get a harmonic series. So this series will diverge by the limit comparison test. And the series that I would compare with would be the harmonic series. Alright, let's try this again. If x equals 1, we have 2 sum k goes from 0 to infinity. Now that I plugged in 1, I just have 2k plus 1. And this is just the same series as before, instead of negative, positive. So this again diverges by a limit comparison test. So that means our new interval of convergence is -1 to 1, not including the endpoints. And go away. And our radius of convergence, just like before, does not change, and I'm still at 1. Alright, and that concludes power properties of power series. Hope you all have a great day. Make sure that you smash the like button and make sure that you like, comment, and subscribe.